Hi everybody, it's Professor Mitchell. Today we're talking about 1.6, transformations of functions. We're covering this section right now because a lot of these concepts are going to be really important in the next two trigonometry sections, which both have to do with graphing. All right, 4.5 is graphing sine and cosine functions, and then 4.6 is graphing the rest of the trig functions. So in this section, we'll be talking about graphs of common functions, and then vertical shifts, horizontal shifts, reflections, and stretching and shrinking. So there's vertical stretching and shrinking, horizontal stretching and shrinking. All right, and then you can do problems that involve more than one of these different kinds of transformations. Okay, so starting with the common functions, these are functions that you encounter pretty often. So we're going to go over each of these. I actually have most of these built in, built into an activity that we're going to do. Okay. The first two functions that you see listed here, I did not incorporate those into the activity. I thought we could just start off by looking at those. But then I believe all the rest of these functions, starting with f of x equals the absolute value of x, you'll see those in the activity. So the first common function that they want you to be familiar with is called the constant function. So understand that this number c here will generally be a given real number. So think like f of x equals 4. Actually, on this graph here, it looks like maybe f of x equals 1.5. See how this horizontal line looks to be about halfway between 1 and 2? So that's a horizontal line. Hopefully you remember from one of your algebra classes that y equals a number, something like y equals 1.5 is a horizontal line. So when you write that using function notation, it comes out to f of x equals 1.5. And that's called a constant function because it only ever takes on one value. Okay, in this case, 1.5. So the domain of this function is all real numbers. If you squash this horizontal line onto the x-axis, you hit the whole x-axis. The range of this function is just the single number c, so I've been using 1.5. I just noticed one nitpicky little thing on here. This c really should have curly braces around it because domains and ranges are always sets. All right, so it's kind of an unusual function. It only has one number in its range. All right, usually the range has a whole bunch of numbers in it. Now, in the trigonometry class, we do not talk about, or at least I don't talk about increasing, decreasing, and constant functions. So you're going to see in the description of each of these common functions, it talks about the function being either increasing, decreasing, or constant. So I'm going to kind of overlook that for now. I might mention at some point just briefly what it means, but I consider this to be more of a pre-calculus topic. And this function is even because it has y-axis symmetry. We'll just put it that way, okay? All right, so that's the first one of the common functions. The next one, which is not incorporated into the activity, is called the identity function. So f of x equals x is using function notation for y equals x. I've mentioned the line y equals x a few times in trigonometry, sometimes when I'm talking about the angle pi over 4. Pi over 4 lies along the line y equals x. So that's called the identity function. The reason it's called the identity function is when you plug in a number x, you get the exact same number out for y. The domain of this function is all real numbers. If you squash it onto the x-axis, you hit the whole x-axis. Whoops, I need to clear my scribble here. And the same thing for the range. If you squash it onto the y-axis, you hit the whole y-axis. And this is an odd function because it has origin symmetry. If you take this side, the right side of the graph, and rotate it 180 degrees, that looks just like the left side. Really briefly, what increasing means is just rising from left to right. As you go from left to right, the graph is going up. If the graph were going down from left to right, that would be called decreasing, and we will see examples of that. All right, so I built several activities into this section. So here's the first one. You have, people watching the video, a handout that you can print that goes along with this. So hopefully you have printed that handout or can print that handout. So it's got this slide on it and all the other ones for the activities. So I think it's pretty self-explanatory. I've given you 3 functions, and I want you to sketch those functions using the tables that I've given you here. So pause the video while you do that, and then we will compare notes. All right, so hopefully you've had a chance to try this activity. So let's look at a couple of the important things that come out of this. First of all, hopefully you came up with something that looks like this. I used a certain website to draw these graphs. So I have a little bit of trouble telling the colors. I think this is blue. The graph of f of x is in blue. Turn my spotlight back on. So there's f of x, and then 2 units above the graph of f in, I don't know if that's supposed to be red or brown or is the graph of g, and then down here in this sort of greenish yellow color is the graph of h. So notice that the graph of g is 2 units above the graph of f, and the graph of h is 4 units below the graph of f. Okay. All right, so let's talk about some things. First of all, this is your official introduction to the absolute value function. I think it's come up in a previous section or two. F of x equals the absolute value of x is the absolute value function. Its domain is all real numbers. Squash it onto the x-axis, you'll hit everything. The range is y greater than or equal to 0. You don't hit any negative numbers in the range. So here's our first example of a decreasing function. Decreasing just means going down as you go from left to right. And this is an even function because it has y-axis symmetry. Okay. All right, so now let's talk about our vertical shifts. All right. The way that you make a vertical shift is by adding or subtracting a number onto the function. So the example that you just did, we started with f of x equals the absolute value of x, and then I added a 2, and that shifted the graph up. And then in another example, I subtracted 4, and that shifted the graph down. So adding or subtracting a number onto the end of the function will shift the graph up or down. All right, that brings us to our second activity, similar to the first one. So I've given you 3 more functions, and I'm asking you to sketch those on the same coordinate system. And I've also given you 3 tables that have pre-selected values of x in them. I don't normally tell you which values of x to use, but I thought, especially for an example like this, that it was kind of important to give you specific ones. Okay. So I'm going to ask you to pause the video and try this activity, and then we will compare notes. All right, so hopefully you've had a chance to try that. Let's see how that looks. All right, so what do we have going on here? Right in the middle in blue is the graph of f of x. This is called a cubic function. And then this is really important because I think this is kind of counterintuitive. Over here in whatever that is, red, purple, brown, I can't really tell. is the graph of g of x. And it is located 2 units to the right of the graph of f of x. And I always make a big deal about that one because it is, I think, completely counterintuitive. The x got replaced with an x minus 2. And what that did was it shifted the graph 2 units to the right. Okay. And sometimes students will ask me, why does that happen? Why does, in this case, minus mean right and plus mean left? I think if you look at how I have these tables set up, it starts to make sense when you stare at these tables for a little while. And then similarly, h of x, the x has been replaced with an x plus 4, and that shifted the graph 4 units to the left. Okay. So now you have an idea. We've already talked about how to shift graphs up and down. This tells you how to shift them left and right. All right. So let's talk about, first of all, the cubic function, and then we'll talk about horizontal shifts. So the cubic function, f of x equals x cubed. Its domain is all real numbers. Its range is all real numbers. Squash it onto the x-axis, you hit everything. Squash it onto the y-axis, you hit everything. And this is an odd function because, again, it has origin symmetry. If you take this piece on the right side and you rotate it 180 degrees, you're going to hit this side. Okay. All right, and then the horizontal shifts, here's how those work. If you want to shift a graph to the left, you replace x with x plus c. So again, totally counterintuitive. Left is plus c, right is minus c. So in our example, the x got replaced with an x plus 4, and that shifted it 4 units to the left. And in the other example, the x got replaced with an x minus 2, and that shifted the graph 2 units to the right. All right, for our third activity, it's the same kind of thing, only 2 functions this time. You have f of x equals x squared, and g of x equals the opposite of x squared. So I'm going to ask you to pause the video and graph those 2, and then we will compare notes. Okay. So hopefully you got something that looks something like this. So in blue, you have the graph of f of x. That's the upwards opening parabola right here. This kind of U shape is called a parabola. I think we've talked about that before. And then the mirror image of that going across the x-axis is the graph of opposite of x squared. Downwards opening parabola, right? Okay, so what we need to do now is talk about the quadratic function, which is f of x equals x squared. And then we need to talk about reflections through the x-axis, which this is an example of. All right, so f of x equals x squared is your standard quadratic function. Its domain is all real numbers. If you squash it onto the x-axis, you hit everything. However, the range is only y greater than or equal to 0. You don't hit anything negative on the y. It's going down on this side, which makes it decreasing, and it's going up on this side. And this is an even function. It has y-axis symmetry. Okay. All right, so what you saw in that example was the standard quadratic function being oh, I know what I did. I've got the vertical and the horizontal reflections sort of lumped together in one explanation after activity number 4. All right, so I promise I will explain both the 2 different kinds of reflections after we go over activity number 4. Okay, so, and that brings us to activity number 4. So I'm going to ask you to try that one. F of x equals the square root of x. G of x equals the square root of opposite x. And I have given you these two tables. So try that right now, and we'll come back and compare notes. All right, activity number 4. So hopefully you've had a chance to try this and gotten something that looks like this. I don't know why my graphing program did not give me a key for this graph. For some reason it put this x from -8 to 8 thing over here. But this over here is the graph of the square root of x. F of x equals the square root of x. And then over here on the left side is g of x equals the square root of opposite x. Okay. So that's an example of a reflection across the y-axis. So a sideways reflection as opposed to an upside down reflection like we had in the last example. And we are also officially introduced to our square root function. So let's talk about that. F of x equals the square root of x is your square root function. Its domain and range are both non-negative numbers, because when you squash this graph down onto the x-axis, you only hit non-negative numbers. You can't take the square root of a negative number, is the interpretation of that. And the range is y greater than or equal to 0 because the square root never comes out to be a negative number, right? This is an increasing function. And this is the first example of one of these common functions that is neither even nor odd. It does not have any of the kind of symmetry that we have talked about. And then as far as your reflection across the y-axis, okay, well, actually, it's going to go over both kinds. So in number 3, we had a reflection about the x-axis. And the way that you make that happen is you just change the sign of the whole function. Put a negative sign in front of the whole function. So the difference when you want to reflect about the y-axis, you just put a negative in front of the x. Okay, see the difference? So square root is a really good example for this. So for about the x-axis, just imagine negative square root of x. That would be a reflection across the x-axis. And then for y-axis, think square root of opposite x. So the negative right next to the x. Generally speaking, when you want to do a vertical thing, you have to do something outside the function. Right? Like a vertical shift, you add or subtract a number onto the end of the function. If you want to make a horizontal thing happen, you have to do something inside the function. You have to do something directly to x. Add or subtract a number to it if you want to do a shift, or make it negative if you want to reflect it horizontally. All right, that brings us to activity number 5. So it's the same kind of thing. I've given you these 3 functions and these 3 tables. So I'm going to ask you to graph these 3 functions on this one coordinate system. Pause the video and we will come back and compare notes. Okay, so let's see how that came out. So hopefully you got something like this. Let me point at some things here. Right in the middle in blue is f of x. F of x equals the cube root of x. It goes over like this, and then it makes kind of a sharp turn up this way, and then it's still the middle one though. Okay. This funny color that I can't decide if it's red, purple, or brown is g of x, and that's the one that over here is on the bottom, and over on this side is on the top. So in other words, imagine grabbing the graph of f and stretching it this way, vertically, okay, away from the x-axis. H of x, which is this sort of greenish color, that one has been squashed down towards the x-axis. That's the one that over here is on top. and over here is on the bottom. It's the one that is always closer to the x-axis. So that one is like taking f of x and going like this, shrinking it down. All right. So these are both examples. Well, one is an example of vertical stretching, and the other is an example of vertical shrinking. But before we talk about that in more detail, let's meet our cube root function. So here is the cube root function, f of x equals the cube root of x. The domain is all real numbers, because if you squash it down onto the x-axis, you hit everything. And the range is also all real numbers. If you squash it onto the y-axis, you hit everything. And this is an odd function, right? You take this piece over here, rotate it 180 degrees, and it's going to line right up with this. It is symmetric with respect to the origin. Okay, let's see. Yes, vertically stretching and shrinking graphs. So what's going to determine whether it's going to stretch or shrink is the size of the number that you put in front of the function. So if c is a positive real number, that number is going to stretch the graph away from the x-axis if c is greater than 1. So this would be like the g of x. From the activity that you just did, it had a 2 in front of it. So the 2 sitting in front of the graph stretches the graph away from the x-axis. However, if the number c is less than 1, but still positive, right? So between 0 and 1, a number like 1/2, that's going to shrink the graph, all right, towards the x-axis. All right, so that brings us to our last activity, activity number 6. So one last time, I'm going to ask you to graph f of x, g of x, and h of x. Oops, spoiler. All right, hopefully you blinked and didn't see that. Using these tables, so I will ask you to pause the video, try that, and then we will compare notes. Okay. All right, so for this one, hopefully you got something that looks like this. Let's talk about this. You already know your cubic function, so we don't have to talk about that again. That's the one in blue, right in the middle. Now here's another one of those counterintuitive ones. If I stick a 2 in right next to the x, what that actually does is it shrinks the graph towards the y-axis, all right? So it almost sounds like the opposite of how the vertical stretching and shrinking worked. Putting a 2 in front of the x shrunk the graph toward the y-axis. Whereas putting a 1/2 in front of the x stretched the graph away from the x-axis. That's the one here in green. All right, so just like the horizontal shifting, horizontal stretching and shrinking is kind of counterintuitive. So let's talk about that. We don't have to talk about the characteristics of the cubic function again because we've already done that. So we can jump right to this. So if you have a positive real number and you stick that number right in front of x, again, horizontal things tend to happen inside the function. All right, and I really want to emphasize if c is a big number, that's going to shrink it horizontally. Whereas if c is a small number, like 1/2, it's going to stretch it. Okay. And again, the difference between this and the vertical stretching and shrinking, to vertically stretch or shrink a graph, you put the number right in front of the whole function. Whereas to horizontally stretch it or shrink it, you have to put that number right next to x.